Zapraszam.
So I would like to tell you a little bit about quantum fluctuations, dephasing in a split BC condensate. First, I would like to remind you a very simple fact that for a gas of distinguishable particles, thermal equilibrium, non-interacting, the variance of atom number difference between a given volume is equal to the mean atom number within this volume. So we say that these fluctuations are Poissonian. Then, because of exchange symmetry, for bosons, these fluctuations are larger, super Poissonian, and for fermions, they are lower. We say that they are sub-Poissonian. This can be observed, these differences can be observed only for very low temperatures. They were first observed in 2005 for rubidium-87 atoms, and then for fermions in 2010 by this group. These super Poissonian fluctuations can be also observed when we split a condensate in an atom number difference between the split halves. And here we have the results of experiment performed in 2010 where they split the condensate. Here we have the experimental setup, this is the atom chip. They held rubidium-87 ultra-cold rubidium-87 atoms in a harmonic, three-dimensional harmonic trap. And then this trap was deformed by changing magnetic field to double well potential. The cloud was stripped completely, and absorption images were taken, and from that the number of atoms was obtained. So what they measured, here we have the plot of variance of atom number difference versus the temperature. Here we have logarithmic scale, and 0 means the Poissonian fluctuations. For very low temperature, they observed that fluctuations are sub-Poissonian. Then temperature grows, fluctuations increase, and they reach maximum at 0.7 critical temperature for Bose-Einstein condensate. Here we have different units, doesn't matter. And then they tend to Poissonian limit. So here this bump is from exchange symmetry, and we can say that this is from interaction.
What does it mean, Poissonian fluctuations in this case?
Poissonian means that variance is equal to number of atoms.
No, to the number.
So it only refers to the variance or to the structure of the distribution?
No, to the variance.
To the variance.
So they are measuring in time, they are measuring the fluctuations, or how?
No, they perform many images after splitting, and from this they calculate the variance.
What value
So the first models to explain this bump and this behavior was proposed for ideal gas, but it neglected the potential barrier. So the first thing which we've done is to include the potential barrier. And here we have our Hamiltonian, kinetic term, the three-dimensional trap, and the potential barrier. Here we have modeled the potential barrier as a delta potential because the eigenfunctions, the eigenenergies of this Hamiltonian are well known. And then in a grand canonical ensemble, we can calculate the variance of atom number difference in terms of second-order correlation functions. So, and here we have the mean atom number in grand canonical ensemble. So the G2 function roughly tells us what is the probability of finding two atoms at places R and R prime. Then, because in graph canonical ensemble the density operator is Gaussian, we can decompose our second order correlation function into first order correlation functions. So we can see that this can be seen as classical term, and this can be seen as a term from exchange symmetry. Now the first coherence function is simply a density matrix, and it can be expanded in a power series of fugacity. Fugacity is exponent of beta times chemical potential.
Could you move your computer a little because it's
okay? So here we have the spectrum of energy as a function of U parameters, so the height of the potential barrier. And because it is a delta potential, it affects only even states of a harmonic oscillator. And here we have, you can see ground state, second excited state, and so on. So as you can see that with growing Q, the eigenenergies increase with Q.
What does it mean that it drops down to zero? There is no ground state for low values of U?
Yeah, this tends to minus infinity, and because this is like a well, so your energy decreased.
Yeah, but there still is a bottom somewhere, so there should be still a ground
no,
state.
it's a delta function.
This is
Positive delta.
Negative. It's on
well,
negative.
on the left it is negative. This is for negative.
Fraction.
Okay.
I would like to show you also how eigenfunctions look like. So here we have the ground state, here we have the ground state of harmonic oscillator, and then we can see how it is deformed when U grows. And we have also second excited state here.
So the second excited state has a maximum at this potential well, at this delta function.
No.
What is? I understand the upper picture, but the lower picture shows that there is a maximum, sort of for at zero.
Yeah, this curve is for harmonic potential, and then it is deformed.
Yeah, that I understand, but that means that even though there is a repulsive delta function, there is still a maximum of the wave function.
Yes, but this is the minimum of the density. Yes. Because you have to square it, the wave function, and then you have the density drops to zero when delta goes infinite.
So here we can calculate the variance using Fick's theorem, and after some integrations we can obtain the variance as a function of temperature, and we can see that we can get this bound. Here this solid line is for U equal to 0, so for harmonic potential. Then these dashed lines are for positive U, so we can see that when U grows, fluctuations also grow. It's quite interesting. And these dot dash lines are for negative U. And when we increase U even higher, in high U regime, we can see that maximum of fluctuation tends to lower temperatures. And this solid line is quite more analytical result for impenetrable potential barrier. So we can see that at zero temperature, for impenetrable potential barrier, there is a very high super-Poissonian fluctuation. So we can extend this also to fermions. And here we have what is the difference, the sign in Fick's theorem. Instead of plus, we have minus. And here we have the curve for harmonic potential. you can see the fluctuations are sub-Poissonian, and here this dotted line is for impenetrable potential barrier, and these dotted lines are for negative U. So when U decreases to minus infinity, the fluctuation tends to Poissonian. So to construct a better model of experiment, we have to include dynamic potential. So now U depends on time, and using adiabatic theorem, we can use this eigenfunction which are known and calculate the variance for very slow splitting, and this is this dotted line. Then for faster splitting, the fluctuation decreases until they reach this limit, which is just instantaneous splitting, and it is the same as without potential barrier.
So let me understand this adiabatic. So you introduce time dependence in U, right? And this is not a function, and this is for different values of t. How does t enter? Or you reach some value.
Yeah. In our model, U is linearly dependent on time, and there is a parameter of speed of splitting, and here we increase just the speed of splitting. You have to then you have to not for adiabatic limit, but for finite speed of splitting, you have to solve Schrödinger equation, time-dependent Schrödinger equation. There's no option, but you can choose.
But the question of Professor Górski was different. He's asking what's the final value of U. Is it infinite or is it finite?
Of course, in simulation it should be finite, but it is so high that the value is impenetrable.
But when you increase linearly, then you have to stop at some point.
Yes.
This is not quite adiabatic. Adiabatic would mean some kind of a hyperbolic tangent or whatever that gives you the saturation.
But is this the stationary state, or this is at some time?
What do you mean?
Well, so there's time evolution, and so is this the value that it reaches at infinite time, or is
That's me.
the distribution at some particular time?
Yeah, we just end the evolution when the barrier is just penetrable. The tunneling is very low. So.
And then of course nothing changes.
But then it's stationary.
Yes, because they cannot.
Because they cannot. Atoms cannot get from one side to the other. The result is the same.
And at this time you plot this curve.
Yes. So the real challenge is to include interactions between atoms, and we used classical field method. And in this method, when the
I
states...
have one more question to the previous slide. Because at the beginning you have the thermal state, so you have some density matrix, and then you evolve this density matrix exactly with to some time, and then you calculate the values. But the final state is not thermal state.
This is related to previous seminar, where this problem was exactly treated.
Yes, but here we have exact solution of...
Jagiellońskie equality.
But here the problem can be solved exactly from the beginning to the end. Because we have exact eigenstates of the Hamiltonian at each moment.
Not exactly, but numerically. So
no, we have exact...
At the end there are exact analytic functions. Because it's completely separate. So these are half oscillators.
Yes, I understand. But it depends on the dependence on time.
Well, the state depends, but the basis on which one can do the analysis is the same.
That I understand, but still the question is how far from the equilibrium is the state that
That's a very good question.
It can be compared to the Jagielloński.
Yes, exactly.
Because harmonic oscillator has this time scale characteristic, the period basically, right?
It's also the, how it's called, splitting? No, I have forgot it, but basically the energy difference
Yes.
divided by h bar divided by 2 pi. That's a time in which the system resolves itself.
It's the period. It's called period.
In harmonic oscillator it's called period.
It's called period.
And that doesn't matter here whether this
Of course, if it's
potential
adiabatic,
goes
of course.
faster or slower.
Yes, adiabatic means that the time variation is
It's
much
much longer.
longer
Yes,
than
that
the
I understand.
characteristic frequency.
But
So
can you
the
sense
answer
it
is-
on this, in these results, or it just smoothly goes from one regime to
And it goes smoothly, as you see, as you have seen.
Okay, so we have used classical
But
field method.
the basis is time dependent or not? in
For
your calculation.
very slow splitting, the most convenient basis is just this instantaneous eigenfunction.
But I think that whole analysis can be done in any regime because
Yes.
we have eigenstates exactly. Okay, of the Hamiltonian. We
Yes,
have
but for very fast splitting, this basis is not very convenient. And
yes, but for each Hamiltonian we have the eigenstates, so you can calculate derivatives of
we can, but
You are right.
we tried it.
What you are saying has been used here, but works very nicely for very slow rating of Grenier. For very fast, it's better to use the oscillator.
Okay.
Sorry, how the spectrum of this oscillator changes when you add delta? Well, whether...
Spectrum, it was shown.
It was shown.
Yeah, but the thing is, okay, for harmonic oscillator without delta, well, the differences in energies do not change, but what if you add delta, because would this difference make some, well, difference of some state of some energy maybe go to infinity, and then the time scale would be, well, the relevant...
Only for negative
time
U.
Time scales that you have to take into account when you do adiabatic theorem.
Yes, you know.
Because you don't start from the ground state, but you start from the terminal state, right? And
Here
you
we
have
see
to
the
take into
spectrum.
account this adiabatic thing for
the right-hand side. You see
all
the-
states, as far as I understand.
Yes, but in principle, the eigenstates of the Hamiltonian at each moment are known, okay? But they are not analytical because they have this cusp. And then it is very hard to calculate the time derivative of such a basis when
Sure, I'm just asking whether maybe, well, some particular energy difference, maybe go to infinity if you add delta, and maybe assumptions that are beyond adiabatic theorem are not valid anymore.
So maybe we'll return to this question later, because time is passing. So what about our method for interacting gases? The single, so when states are occupied by many atoms, we can treat annihilation operators and creation operators as a single complex numbers. So instead of field operator, now we have single valued complex function, which we call classical field. And the energy of this field is given by this functional. So here we have kinetic term, the potential, and here we have the coupling of contact interaction. And then, because we are going in the direction which is reversed to the Max Planck's direction, we have to encounter the catastrophe in ultraviolet. And to avoid this catastrophe, we have to introduce a cutoff. What more, when we want to restrict the number of atoms, we have to use this normalization condition on alphas. And when we want to construct the ensemble of thermal ensemble of classical fields, we have to distribute them in phase space according to this probability distribution, Boltzmann probability distribution. And the best way to do it is the Metropolis algorithm. So it is a Markovian process. We start with a single point in a phase space, and then we walk randomly in this phase space, and some of these points visited during this walk are included to our ensemble. So So the last question is the choice of the best cutoff, and this choice, this was proposed in previous work by Tomasz Górski, and it occurs that for one-dimensional harmonic potential, it looks like this. So when temperature grows, we have to include more states. So we can go back to our question, how to calculate the variance for interacting gas. At first we have to construct the canonical ensemble using Metropolis algorithm. Then we have to evolve each of this classical field by time-dependent Rosputeyevsky equation with rising potential barrier, here, and the interacting term is here. And at the end we have to calculate the atom number difference, so we have to calculate the integrals like this, classical fields. So at first we have calculated this without splitting, and here we have variance versus temperature. The solid line is for ideal gas in ground canonical ensemble. So our previous result, and here we have results for interacting gas. You can see that fluctuations are lower because atoms repulse themselves. What is more interesting is that maximum of these fluctuations is shifted to our high temperature, and it is just like experiment. It was also shifted.
How many alphas did this calculation involve?
It depends on the temperature. So it's given by scatter.
Roughly how many?
So here maybe 100, here maybe 5, 10. And we have calculated also the variance for dynamic, for splitting. And here we have also variance versus temperature, and these open circles are measurements, are results for very slow splitting, and these crosses are for fast splitting. So we can see that for faster splitting, the fluctuations are higher. So the next question is that in a real experiment, the absorption image is taken, and it is always taken in a finite time. So maybe we do not have to take into account instantaneous classical field, but time average density matrix. So here we call them coarse grained. Here delta tau is just the time of averaging. And it occurs that this quantity, coarse grained density matrix, reflects very well the coherence between split clouds. So for ideal gas, here we have 3 images of coarse grained density matrix for 3 different averaging time, increasing. And for the ideal gas, you can see that values of coarse grained density matrix in these off-diagonal quadrants do not decay with time. So the coherence is preserved. But for interacting gas, which is very interesting, this coherence is lost with time. So at the end, for very long coarse graining, we can see that this is not superposition of atoms in this and this well, but they tend to localize each well.
How is the averaging time related to the frequency?
So the averaging time for one-dimensional gas is quite long, but we hope that for a three-dimensional model, it would be shorter.
But in your
It's not
calculation,
related to the frequency, it's related to interactions.
no, but it can also be related. My question is it much longer?
Much longer.
Much longer. Because here there are several time scales.
Yes.
So we can also perform this this was very low temperature. And for higher temperature, we can also perform this averaging, and this is the result for ideal gas, and this is the result for interacting gas. You can see that density matrices are more intricate in this for high temperatures, and you can also see that for ideal gas, for long averaging time, there is always this coherent part, and for interacting gas, it decays.
Why there is no symmetry with respect to reflection?
No.
To this diagram, no reflection.
No, tak jest napisane.
Because the state is not exactly.
Here, no, in this direction, the symmetry is not needed.
No, I mean in this direction there should be symmetry.
To są koherencje.
No.
The left and right world is not identical.
It's not identically populated. But there is symmetry with respect to the diagonal.
Here we have this symmetry.
Of course.
In this direction we do not have, but
Yes,
it can be not
To
symmetrical.
są koherencje.
Okay.
So this is not a thermal state in the sense.
No,
This
it's
is
one example.
One
Yes.
One copy.
initial. So this is
Very
any state. We can say this is any state.
Yes.
It is not for thermal states. It's for any state.
Yes.
So then we check how this density matrix depend on the final height of potential barrier, and when this final height is large and the potential barrier is impenetrable, the coherence is lost, and when we decrease this potential barrier, you can see that coherence is restored, and at the end here we have the image of without splitting.
Just harmonic oscillators.
Yes.
To further analyze this coherence between these two split parts, we diagonalize the coarse grain density matrices, and it occurs that without splitting, there is one dominant eigenvalue. But after splitting and sufficiently long coarse graining time, there are two dominant eigenvalues, and they correspond to the eigenvectors which are localized in the left and in the right value. And what we can get also from this density matrix is the population of the orbitals. So these eigenvalues, you can see them as a population of the orbitals for atoms, so this Ni.
But these are interacting orbitals.
Yes. But also defined by the observation time. And that's the peculiarity of this approach.
So then we can calculate the variance for the single splitting, single classical field. We can calculate we call them quantum fluctuations like this. And here we have this variance for Poisson distribution. And for low temperature, here are our results. These are these red dots, and we can see these oscillations. Because we are at very low temperature, we can use two-mode model and obtain variance from this two-mode model. And we can see that these oscillations are also seen in this two-mode model. And the time of this oscillation period is similar. The amplitude is a little bit.
So what is the period here? This is given by what characteristic time?
This is the difference between chemical potentials on the left and the right wall. And for higher temperature, this looks there is no oscillations, but just monotonic decay for interacting gas. And for ideal gas, we can see that this function of variance is constant, roughly constant. So we can see, once again, we can see the large difference between interacting gas and the ideal gas. We do not understand why this difference, why it originates, but
Well, we do understand. Come on. There's a lot of
analytically we do not understand.
What is the meaning of these huge jumps here? For example, at point 6 you have...
I don't know. They just my result. Maybe it is.
No, but there should be either this is a new effect or it's the error in
You can see the
calculation.
point, and there are many. There are many points which are a little bit higher, a little bit lower. So maybe it's just fluctuation. I don't know why this point is here.
This is huge. I mean, there should be some... Is this a numerical fluke?
Maybe.
Maybe
No, but I'm talking about point 6, where there are points which differ by, what, 50%?
So this is our last result, and it will be very interesting to check this experimentally, this dependence of variance on the time of imaging. So experimentalists can extend the time of laser pulse and check if there is the effect like this. So with this I would like to end. Thank you very much.
Thank you.
So does that mean that if they average over a long time in the experiment, they'll see like number squeezing? I don't understand that.
Yes, we expect that there will be some dependence on the duration of observation.
So that would mean that number squeezing measurements that they've done is actually just time averaging and not new number squeezing.
I don't know if this term squeezing is good here, because there is no entanglement here. I think it is a different effect.
Well, okay, I mean subpulsonic fluctuation.
Squeeze.
I have to say that's quite surprising.
Yes, we agree.
If there are correlations between spatially separated regions, then there is an entanglement, I would say.
But we are trying to show that at the end, when time of cross-graining is very long, there is no correlation. This system is like a classical system.
If there are no more questions, we thank the speaker.